All right, for our next talk, we have Eugenia Colafranceschi telling us about I von Neumann Algebras, gravitational mathematics.
Thank you very much to the organizers for the opportunity to speak here. I'm presenting today a work in collaboration with Shidong, who is here, Donald Marolf and Zhencheng Wang, who is also here. A work about gravitational entropy as given by the Ryu-Takayanagi formula from a purely bulk perspective, so without relying on holography. Okay, so in the anti-de Sitter conformal field theory correspondence, we have the Ryu-Takayanagi formula, which is a prescription to compute the entropy of a bulk region in terms of the area of a minimal surface in the bulk plus corrections. And in 2013, Lekovitz and Maldacena showed that the Ryu-Takayanagi formula can actually be derived just from the gravitational path integral. But yet, an interpretation of this formula as a standard entropy still required an holographic dual theory. And so here's the question: if we don't know whether our gravitational theory has a dual field theory, what does the Ryu-Takayanagi entropy compute? And is this an entropy, and entropy of what? There has been a lot of progress recently in these directions. And in particular, several works have shown that in various contexts, the Ryu-Takayanagi entropy can be derived as an entropy of a type 2 von Neumann algebra. So this provides what we might call a statistical interpretation for the Ryu-Takayanagi entropy, thanks to the type 2 trace. But this is still not what we have for a standard quantum system. For a standard quantum system, we have an entropy in terms of a Hilbert space trace, so a trace which is given by a sum over an orthonormal basis, and that which provides what is a state counting interpretation, essentially. And in terms in the language of von Neumann algebras, this Hilbert space trace is a type 1 trace. So the main question behind this work is, can we understand the Ryu-Takayanagi entropy in terms of a standard Hilbert space trace? And so provide a state counting interpretation for it. Okay, so let's be more concrete. Consider a gravitational system with two asymptotic codimension 2 boundaries, so a left one and the right one. Now, the Hilbert space for this gravitational system a priori does not factorize, as pointed out by Daniel Harlow some years ago. Now, in particular, if we have an holographic dual theory, then the Hilbert space does factorize into a Hilbert space associated to the left boundary and a Hilbert space associated to the right boundary. And then there is a precise sense in which we can associate a state counting entropy to the left or to the right boundary. But as I said, in this talk, we are not going to assume the existence of an holographic dual theory. And so we might say that our goal is to construct from bulk arguments a Hilbert space, or we will see this in which way this will be realized, but you might think that the main goal is to associate an Hilbert space to this left boundary such that the corresponding Ryu-Takayanagi entropy can be understood in terms of a standard entropy for this system. And in particular, so we have the usual trace rho log rho, in which this density matrix associated to the left part is obtained by the state for the full system, just tracing out the right part. And we found that this type of structure is present in any UV complete asymptotically locally anti-de Sitter theory of quantum gravity, anytime the Euclidean path integral satisfies a simple set of axioms. So here is the outline of the talk. I will start by listing the axioms for the path integral. Then I will show how to construct a Hilbert space from this path integral, how to define an algebra of observables from it, and then the proof that this algebra must be composed of type 1 factors, and finally how this structure leads to a Hilbert space interpretation for the Ryu-Takayanagi entropy. Okay, so let me start by defining what we have in mind when we talk about an Euclidean path integral. So as I said, we consider a UV complete asymptotically locally anti-de Sitter theory of gravity. And the Euclidean path integral is an object that associates to every space-time boundary, so every codimension 1 boundary, a complex number that you might think as given by all possible geometries, topologies, and matter fields that satisfy the given boundary conditions. So here I introduce the notation I will use throughout the talk, in which the boundary manifold also includes a choice for the boundary metric and a choice for the matter fields on the boundary. So this is something you might have in mind for your Euclidean path integral. And so here I'm just building up some intuition for the axioms. I will then make precise in the next slide. So you might expect this path integral to be finite, to be continuous, and to be a real function of your of possibly complex sources. So when we can slice our path integral along a surface, and in particular, this surface sigma will intersect the space-time boundary along a codimension 2 surface, this partial sigma. And with this slicing, we can interpret the path integral as computing an inner product between 2 states, the states prepared by the boundary conditions on the lower part and the boundary conditions on the upper part. So computing an inner product on this Hilbert space, which is associated to this codimension 2 surface. And in particular, in case in which the lower state and the upper state coincide, we expect the path integral to compute the inner product of the state, and so the result to be positive definite. Okay, so let's look at the axioms. So the first one, we expect the path integral to be finite, so to be a well-defined map from boundary conditions defined by smooth manifolds to the complex numbers. We expect it to be a real function of possibly complex boundary conditions, as I showed before, to be reflection positive. Then we introduce a continuity condition, a very weak one. So we assume that anytime the boundary manifold has a cylinder of a certain size, the Euclidean path integral is continuous under under the formation of this size for the cylinder. And the last axiom we assume is the factorization. So when we have 2 closed boundaries, the path integral for the disjoint union of these 2 boundaries is just the product of the path integral for the first one and the path integral for the second one. Now, let me remark that in all cases in which your path integral is expected to be a collection of what is called baby universe superselection sectors, then this factorization is expected to hold sector by sector. And so our analysis can be applied in that sense. Okay, so let me move to the Hilbert space definition from the path integral. As I mentioned earlier, when we cut open the path integral, we have 2 pieces that we can interpret as preparing some states. And in particular, the 2 boundary manifolds, indicated as N1 and 2, share the same codimension, so the same boundary, which is a codimension 2 surface in our theory, this partial n here. And the path integral again is expected to compute the inner product of these two states. So if we want to now have a formal construction of our Hilbert space, so we want to have surfaces like this defining states, and the full manifold obtained by gluing these surfaces back as computing the inner product, we should take care of some subtleties in this procedure. So in particular, we want the gluing of these two surfaces to be uniquely determined, and this might not happen in case in which this codimension 2 surface has some symmetries, for example. And also, we want the gluing to produce smooth manifolds. So for these two reasons, we want the points on this partial n to be labeled, and also to come with a rim. So we introduce this additional requirement that every codimension 2 surface, which is the boundary of our source manifolds, come with this rim of a certain size, which can be taken down to 0. Okay, so once we start with this set of d-dimensional manifolds, I'm assuming here that our theory of gravity is in d+1 dimension, so d-dimensional manifolds are codimension 1. So we have these surfaces with this boundary that comes with a rim, and then we can associate to each of these surfaces a state in a pre-Hilbert space with the inner product defined before. And then to have a Hilbert space, we can just take the quotient by the null states and then complete the result in the usual sense. And so this is a proper Hilbert space defined. Yeah? A rim means that in this case, there is a cylinder, a small, that the part close to this codimension 2 boundary is diffeomorphic to a cylinder of a certain size, epsilon. And these, so these are guarantees that the gluing is then smooth. And you can take the cylinder to have a arbitrary small size, but
not a condition on the extrinsic curvatures.
That's a condition on these boundary manifolds, on the boundary conditions that you have. Okay, so we define this Hilbert space. Now let's move to the definition of operators from this path integral. And in particular, we want to specialize to the case in which the codimension 2 surface is formed of two components. And so we want to consider surfaces of this form in which you can look at the two components like an input and an output boundary, and to construct from this an operator that acts and preserves some sector of the Hilbert space. And again, I will make this precise later, but this is to give you an idea of what is going on. So, and why we want to now focus on surfaces. We have this boundary with two disconnected components. So let's consider the set of these two boundary surfaces. We can define on this set a left product and a right product. So in particular, if you imagine to label these two boundaries as left and right, and you have these two elements A and B, the left product will be given by gluing the left boundary of B to the right boundary of A, and the right product the other way around. So the set of the d-dimensional surfaces with these two B boundaries equipped with the left and right product defines what we call a left and right surface algebras. There is a natural involution on this algebra, which is we refer to that as a star operation, in which you complex conjugated sources and you swap the left and the right labels. So, and we are going to see that there is a precise sense in which the left surface algebra acts on the left boundary of the Hilbert space sector, and the right surface algebra acts on the right one. Here is so the algebra equipped with the left product and the algebra equipped with the right product. So crucially on this algebra, we can define a trace operation. This trace operation is given by gluing together the input and the output boundary of our surface. And so having a path integral that is computed with the boundary manifolds given by the closed manifold resulting from this gluing. And from the dictionary we built between rim surfaces and states, we then have that the inner product between A and B states is just the trace for the A star element and the B element. And so is the path integral computed on this surface. In particular, when we have the inner product between, when we have the inner product for two states and we are computing the normal, thanks to our positivity action, this is positive definite. And this property is going to allow us to derive a crucial result, which is a trace inequality for our path integral. So far we talk about a Hilbert space with two boundaries, but we can actually use the surfaces A and B in our set to define elements of a four-boundary Hilbert space. And so here is the example. So if we take two boundary surfaces A and B, you can construct these two states in the four-boundary Hilbert space for in which I label the boundary as left one, left two, right two. And we have these two states that, as you may see, are related by the action of a swap operator between a right boundary and the left boundary. So with these two states, we can then consider the norm. And just from this graphical picture, you can already realize that the norm of these two states coincide. So it's given by in particular, the product of the path integral for these two disconnected boundary manifolds. And then we can apply the Cauchy-Schwarz inequality, which is a standard consequence of the positivity of the inner product on this four-boundary Hilbert space. And so we derive this trace inequality for our path integral. And this is the result that will then allow us to reveal the structure of our Hilbert space. But before going there, let's consider a representation of this algebra on our Hilbert space. So far we talked about an abstract surface algebra. So in particular, to any element of this surface algebra, we can associate an operator on our Hilbert space, which acts just with the gluing of the boundary to the boundary of our state. And so the resulting state is just the one defined by the full surface. And thanks to the trace inequality we derived in the previous slides, we find that these operators are bounded. So you can just write the operator norm, apply the trace inequality, and see that you have this bound. So we have a representation of the surface algebra in terms of bounded operators on the Hilbert space. And of course, there is a corresponding representation for the right algebra. So now we specialize to the diagonal sectors of the Hilbert space, meaning that we consider the two B boundaries to be the same. And this allows us to consider elements which are just the cylinders I already mentioned for the rims. And the cylinders in this Hilbert space allows us to define a trace operation on this representation algebra. So we have that for a given element, a given operator in this Hilbert space, the trace is just given by gluing these cylinders and take the limit in which the size of the cylinder goes to 0. So in this diagonal sector, we have a precise definition of what is the trace as induced by the path integral trace. Okay. So we can then define, so once we have these surface algebras and a representation of this algebra on the Hilbert space, we can define von Neumann algebras to be the closure of this representation algebra on the set of bounded operators on the Hilbert space and the weak operator topology. And in particular, we can show that the trace defined on the representation algebra can be extended to all positive elements of this von Neumann algebra. And in particular, we can show that the trace is faithful, so essentially non-degenerate, is normal, so there is a sense in which it's continuous, and is semi-finite, which basically means that not all non-trivial operators have infinite trace. And also by using an extension of the 4 boundary arguments I showed before, we have that the trace inequality also on this von Neumann algebra. Okay, so from the trace inequality, we can derive the key result, which is, so first, when we apply the trace inequality to, and we apply it to a projection in this von Neumann algebra, we get that the trace of the projection is bounded below by 1. And since, so let's review some known results on von Neumann algebra. So we know that every von Neumann algebra is a direct sum of factors, so of algebras with trivial centers that can be type 1, type 2, or type 3. But there is no faithful normal and semi-finite trace on type 3, so we cannot have type 3, because we proved that the trace on this algebra is faithful, normal, and semi-finite. Moreover, on type 2, for any faithful, normal, and semi-finite trace, there are no non-trivial projections with arbitrary small trace. And since we derived this bound for the trace of a projection, we can exclude type 2. So this means that our algebra can only composed of type 1 factors. And in particular, the commutation theory for semi-finite traces also tells us that these left and right algebras are commutants on this Hilbert space. Okay, so we can further show that the central operators for the left and the right algebra have purely discrete spectrum. This means that when we simultaneously diagonalize all central operators in the algebra, then we obtain eigenspaces such that the Hilbert space sectors decomposes in this way. So it's a direct sum of these eigenspaces. And the von Neumann algebra, as a result, also decomposes in this form. And for what I showed before, we can only have type 1 factors. So now we know that this algebra for a given factor is a type 1 factor, and as a commutant, this right factor on our Hilbert space, diagonal sector for the Hilbert space. And so in particular that we have this additional condition on our Hilbert space that it decomposes into tensor products of Hilbert space for the left part and a Hilbert space for the right part. Okay, so once we have this structure for the algebra and the Hilbert space, we can then talk about an entropy for this algebra. So let's in particular look at the normalization of the trace. So we know that faithful normal and semi-finite traces on type 1 algebras are unique up to an overall normalization constant. And so we have this relation between the path integral trace and the trace on the Hilbert space. So we have this constant C mu. And in particular, if you consider as element of the algebra a one-dimensional projection, so we know that the trace in a given mu sector is just 1, then we have this relation for the trace, the path integral trace for the projection, and this constant C mu. And in particular, as you recall, we derived from the trace inequality the condition that the trace of the projection is bounded below by 1, which means that this constant is bounded above by 1. Now, the trace inequality was a consequence of the positivity of the inner product on the 4-boundary Hilbert space. And so the amazing result is that by looking at positivity of the inner products on Hilbert space for larger number of boundaries, we can actually further constrain this constant here. So indeed, from the positivity of the inner product, what we actually get is that the trace of a projection can be 0 or bounded below by 1. And then if we consider the Hilbert space where we have n copies of our 2 boundary system, then what we have is that the trace for the projection is a positive integer between 1 and n minus 1. And so we have a recurring argument which tells us that the trace of a projection is a positive integer. So this means that the constant that is setting the normalization for the and the relation in particular between the path integral trace and the Hilbert space trace satisfies this relation. And so what we can do is to define an extended Hilbert space. So in particular for any Hilbert space factor, we introduce this what we call an hidden sector, so that we have this full extended Hilbert space, which is just given by the tensor product of an extended Hilbert space for the left boundary and an extended Hilbert space for the right boundary. So then, thanks to this, we have that our path integral trace can actually be interpreted as a standard Hilbert space trace on this extended Hilbert space. So in particular, when we consider an element A for a given sector of the algebra, the 2 traces coincide once we consider an embedding of this A element in this way. So we consider the tensor product with the identity on one of these hidden sectors. And so the hidden sectors, as I said, allow to interpret the path integral trace as a standard Hilbert space trace. So, so what we have now is that this trace can be used, so the path integral trace can be used to define a left entropy on a pure state of our Hilbert space. So in particular, once we have this state and we can construct a density matrix from here, we can then embed the density matrix into the extended Hilbert space and just compute a von Neumann entropy in the standard way. And now, thanks to the relation between the path integral trace and the trace on the extended Hilbert space, we have that the entropy is given by standard von Neumann entropies on each sector plus a mixing term for the probability of the state of being in each sector separately. And we can then compute this entropy via the replica trick. So in particular, once we have the state, and we can so consider the density matrix, we can apply the replica trick, and then we can follow the prescription given by Lekovitz and Maldacena to compute an entropy for the state. And we know that in the limits in which the theory, the semiclassical limit, when the theory is described by Einstein, Hilbert, or JT gravity, this entropy is given by the Ryu-Takayanagi formula. Okay, so let me conclude. So we have shown that any gravitational path integral that satisfies a simple set of axioms define von Neumann algebras of observables which are associated to codimension two boundaries, left and the right one. These algebras contain only type 1 factors. And as a result, the Hilbert space on which this algebra act decomposes into a direct sum of a factor associated to the left part and a factor associated to the right part. The path integral trace is equivalent to a standard trace on an extended Hilbert space, thanks to the quantization rule we derived from positivity on the Hilbert space. And so in particular, this provides a space, an Hilbert space interpretation for the entropy, even when the gravitational theory is not known to have a dual holographic theory. And so we have this expression for the entropy, and we know that in the semiclassical limit, when there is a precise sense in which the limit is described by Einstein, Hilbert, or JT saddles, this entropy is given by the Ryu-Takayanagi formula. So thanks for the attention.
So many examples of the ADS-CFT correspondence, your axioms hold when the boundary has positive curvature, but they don't hold if the boundary has negative curvature because the Euclidean path integral diverges there. So is that a problem for you, or can you just restrict to those cases somehow?
So we expect, so in the case in which the Euclidean path integral diverges on these cases, so our axioms define a precise sense in which this gravitational theory can be, we can attribute an entropy to the boundary, and we expect actually the axioms to be satisfied. I mean, they are not enough, of course, to define a CFT, but they're expected to hold in a CFT. So I guess that
they don't hold if the boundary has negative curvature. So the question is, can you still do something even in those cases? Those are examples like that.
Because of the R phi
The
squared
axioms are
term.
just too strong. So
There's a R phi squared term in the action for R is negative.
So is there a weaker version of your axioms that can still work in those cases?
Well, I guess.
Yes, right.
Yeah, the point is that if the finiteness of the action fails, then this construction doesn't apply, of course. So I don't know. I don't have a good answer to that. I should think about it.
Oh, yeah, question.
Hi, I have a question. So typically in gravity, when we cut and glue subregions, there is a huge redundancy that is expressed in the fact that there are symmetries at the interface. So these are these extended corner symmetries group, that what they are doing are just inferring the gravitational constraints. And therefore, if I take two Hilbert spaces in two subregions and I glue together, I cannot just take the tensor product because it would be too big. It will not take into account the fact that I am actually imposing some gauge constraints. And so I cannot perform independent measurements in the two subregions. I don't understand whether perhaps it's this ring condition that you're putting on your corners that is doing that magically, but how do you end up having type 1 factors? How do you take into account the no locality of the gravitational gauge constraints into the theory?
We are, the first thing is that about the redundancy we have in case of symmetries, so we consider the points of these boundaries to be labeled, so that in case of symmetries we get rid of the fact that the gluing is not unique. But also we are considering asymptotic boundaries, while I think the cases you were mentioning would be problematic in the case when we consider finite boundaries in the gravitational theory. Right, yes, so here we have asymptotic, so we are considering two asymptotic boundaries which are closed. So also, I mean, also in just quantum field theory, if you consider the full asymptotic boundary of your Cauchy surface, you expect type 1.
Why should the boundaries be asymptotic? Why wouldn't your axiom be true even when the boundaries are at finite location?
Well, a first problem I think would be what Luca was mentioning about.
Luca was mentioning is only if you are gauging the differential prisms on the boundary. But let's say we don't gauge the differential prisms on the boundary and we put the boundary at the final location. Perhaps these axioms would still be true.
I think. Well, I think you would restrict a lot the analysis, because in that case, for example, I mean, you have in mind something like gravity in a box in which we have just gravity inside. Okay, no, in that case, the actions should hold equally well, yes.
Question? Yeah, but then wouldn't you worry that the dual theory would not be well behaved and causal? You have all sorts of pathologies.
Sorry?
If it's gravity in a box, and if it's finite box, then it will have all sorts of.
Well, of course, it would, I mean, in this case, we are assuming smooth manifolds in the Euclidean setting, smooth boundary manifolds. So, I mean, in the Lorentzian case, of course, you could have, you should include then some boundary configurations which are singular to generalize this.
Yeah, I just wanted to follow up on this idea that we were, we don't start with it as a part of boundary. So, fine entanglement wedges for arbitrary regions, arbitrary spacetimes, and they obey the properties that would make you think they, for example, compute a von Neumann entropy and so on, like strong solidity. And so I think it would be extremely interesting if you can extend this approach to explain why that happens. I mean, it sounds like this. It's not clear to me what the obstruction would be, but I don't understand it well. But it would be very interesting because you could try and reverse engineer, some statements about quantum gravity in space-time enough to space-time.
Could you? I didn't quite catch why you used it was quantum gravity. I mean, the same rules could presumably be applied to an ordinary quantum theory.
Yes, the reason why, yes, of course. I mean, the reason why we are looking in this context is because in the case of quantum gravity, your Hilbert space a priori does not factorize, and so you are interested in if there is a meaningful sense in which you can associate an entropy to a subregion defined by these asymptotic boundaries. In quantum field theory, you can just put a regulator and your Hilbert space as a sort of effective factorization. So the setting there is clear. It's not clear in the gravitational setting.
So then conclude that an ordinary quantum field theory is type 1? Or?
Well, you consider the asymptotic boundary is type 1.
Yeah. Okay, so that would be just another one.
Yeah.
In regular ADS-CFT, we expect that the algebra associated to each boundary is a single type 1 factor, right?
And I think you proved that the algebra associated to each boundary is a product of type 1 factors. What additional assumptions do you think you need to make to get to a single type 1 factor?
So
I think the distinction is important because, for instance, JT gravity satisfies all your axioms, but even in the pure case, and in that case, you know, the fact that you get a type 1 factor is a bit trivial because it's just a product. Each factor is just a product of each individual energy. So I think to get the answer in the CFT, you really want the single type 1 factor.
You mean a sum, not a product, right?
Sorry?
Do you mean a sum, not a product?
That's a sum.
well, indeed, in pure, yeah, because if the algebra, I mean, the sum over sectors is the result of the, I mean, of the diagonalization of the central operators. And in the case of JT, the algebra is trivial, and so you have just a one-dimensional Hilbert space. So in that case, it naturally reduces to only one sector.
Well, JT does not obey the axioms, as is seen by the fact that, let's say, in JT without matter, you have a continuous center, not a discrete center.
Yes, I was referring to the fact that if we just want to look at what the algebra we have in pure JT and which kind of central operators we have, and we analyze them, then it's.
It doesn't factor. The way it happens is that JT at very low temperatures, it won't work. It doesn't have the properties of type at very low temperatures.
Just to clarify, when I said that it holds, that it satisfies your axiom, I thought you mentioned that you could go to a single member of the ensemble.
Yeah.
In your first slide, and I think then it satisfies your axiom because the Hamiltonian has a discrete spectrum.
Exactly. It's sector by sector.
Yeah, so so good, the axioms. So these axioms look to me quite similar to what I might want to write down as formal axioms for defining what I mean by conformal field theory. So do you think there are things that aren't just boundary conformal field theories that obey these axioms? Or are we just
for example, one point is that we didn't include anything about the locality of your CFT.
Or assumptions about locality?
Yeah, but it's a mild factorization about the two asymptotic boundaries. So it's true that we would have.
Sure, but like, for example, in the Siegel axioms, the way locality is imposed is this a rule for how gluing works, which kind of feels similar to 4 and 5. But certainly reflection positivity is very powerful. Yeah, I mean, I feel like several of these axioms are very non-obvious from the bulk point of view.
Yeah, of course.
They're obvious from the boundary point of view, but I feel like they're almost just putting in the boundary CFT. So that's why I'm curious if there are things other than field theory that obeys the axiom.
It's true that you see this as saying, okay, once you assume these axioms, of course, your bulk gravitational theory is as much area CFT as possible. Yeah. But yeah, the factorization is a very strong condition, but well, as I said, you can expect to apply only sector by sector. So you could expect the theory to be a collection of sectors in which this is realized. But yeah, they are, of course, I mean, from the boundary perspective, very natural. I agree.